start recording on your computer.
Recording now.
Okay. Okay, thank you very much. My name is Dr. Nasser Ali, and on behalf of, would like to welcome you on behalf of Young Professional Society YPS. We have welcome you all to this very important webinar, and also we have a very important young scientist who's making a lot of headlines in the media for his achievements. And our speaker will be speaking about a very, very important topic, graphene. And Dr. Yarjan Samad is based at the Cambridge Graphene Centre at the prestigious University of Cambridge in the United Kingdom. And it was in 2010, about exactly a decade ago, that the Nobel Prize in Physics went to the two scientists from the University of Manchester, and for their groundbreaking work on graphene. And since then, the interest in graphene has intensified. There's a graphene center that was built at the University of Manchester, and there's a lot of good work that's been going on. And even it attracted the Chinese president to come and visit the graphene center in Manchester several years ago for the potential of graphene in different application areas. So a lot's happened since the Nobel Prize in 2010, and scientists have looked beyond graphene in terms of developing novel graphene-related materials and new application areas. And Dr. Yarjan today, he will be speaking about the application of graphene in space. So I was supposed to share some slides to tell you a bit more about the Young Professional Society, but unfortunately my laptop is not working, so I'm on my mobile, so I'm not able to share. But if you want to know more about the Young Professional Society, the sort of work that we're involved with, you can actually see us. We have a website, www.ypsociety.uk, which will give you information. There's blogs there that you can read, and also tell you how, if you're interested in becoming a member of the society, and how you can become a member. We're also on Facebook. You can see us on Facebook, on Instagram, on LinkedIn as well. And as we speak, this webinar is being live streamed on Facebook. And so those people who are joining us from on Facebook, welcome to you. And you can actually ask Dr. Samad, our speaker, some questions. If you do have any questions, you do type them in the comment box, please. And those of you who are joining us on Zoom, if you've got any questions, at the end, I'm sure Dr. Samad's lecture will last for about 45 minutes or so, and then we'll have some questions time as well. So if you've got any questions, type them down, and they'll be answered. And we're very, very pleased to be partnering with the STEMatters, an organization doing excellent work, who are based in the States, in Texas. And through them, hopefully we'll have some of our colleagues joining us from the United States. So welcome to you if you're joining us. And this webinar will be live streamed on STEMatters timeline on their Facebook page as well. And the YPS actually focuses on 3 areas. And these are the 3 pillars that we work under: communication, leadership, and innovation. And so I think without further ado, I'm going to pass over to Professor Waqar Ahmed, who is based at the University of Lincoln and is also the president of the Young Professional Society, who will introduce our speaker and then conduct this webinar. So thank you very much. And Professor Ahmed, if you could introduce our speaker. Professor Ahmed, if you could unmute yourself.
Can you hear me now? Hello?
Yes, we can hear you.
I'm delighted to introduce Dr. Yarjan Abdul Samad. He's got a long list of achievements. I'm going to try and just summarize them and give most time for the scientific work he's done with the European Space Agency. So Dr. Samad is a senior research scientist and a teaching fellow at the University of Cambridge, the world-famous Cambridge Graphene Centre. His research is based on space technologies, and he was amongst a team of scientists on the European Space Agency Zero Gravity Flight, who were the first to test graphene, a modern-day marvel material in zero gravity. Besides doing experiments in zero gravity flights, he's also performed experiments in sounding rockets. Dr. Samad and his team is slated to take their experiments to the International Space Station in collaboration with the Microgravity Research Centre in Brussels, European Space Agency, and other European partner institutions and private sector organizations. His invention on cooling devices in space has been covered by international media, including but not limited to Reuters, TechRadar, CNET, InnovaSpace, and so on. He has won many awards for his research, such as Innovator of the Year by the Technology Development Company, the Outstanding Research Reviewer of the Year by the Royal Society of Chemistry, Nano Today Best Scientific Presentation, and many other best scientific talks at international scientific conferences. In addition to his research, he teaches graphene technology at the University of Cambridge, supervises numerous master's and PhD students. He also lectures at several other international academic institutions, such as Chalmers Institute of Technology, University of Manchester, and also at the University of Lincoln. He's co-authored a book and about 60 international refereed scientific journal papers and many conference proceedings and presentations. He's a guest editor of the scientific journal called Sensors. Prior to moving abroad, he obtained his bachelor's degree at the famous Ghulam Ishaq Khan Institute in Pakistan. He holds 4 patent applications, and he graduated from the Ghulam Ishaq Khan Institute with 2 gold medals, one for best academic performance, another for best overall performance. Dr. Yarjan belongs to Baluda, a village near Turbat in Balochistan, Pakistan, and has acquired his early education from his native village. So without further ado, I'm delighted to introduce Dr. Yarjan.
Thank you, Professor Waqar Ahmed, for the very kind introduction. And I think I can share my slides now. So can you enable me to share my slides, please?
If you can make Dr. Yarjan the co-host.
Thank you. Okay, so as the introduction has already been done, so I'll just move on with my talk, which is about graphene for space and beyond. So the outline of the talk is as follows. I'll first of all talk a bit about the University of Cambridge and why we are talking about space and the problems in space, why graphene in space, and sensing with graphene. This is one of the applications of graphene that we are working on, and followed by conclusions and question answers if you have any. So first of all, University of Cambridge is composed of about 31 colleges, and there are old colleges, new colleges. There are colleges which were built between 12th century and 15th century. These are called the 16 old colleges, and then there are 15 new colleges. which were built from the 1800th century until 1977, when the last college was formed. And then there are some other colleges, for example, Clay Hall, Darwin, Hughes Hall, St. Edmunds, and Wolfson, which are basically postgraduate only colleges. And then there are some colleges which are female only colleges, for example, Murray Edwards, Newnham, Lucy Cavendish. So a college basically in Cambridge is not the same concept as in many other countries where college is based on the subject, for example, engineering or maths or physics and things like that, or humanities. In Cambridge, a college is more like a community which provides a lot of facilities to the students, and it connects the students from different fields together. So, and under the umbrella of the University of Cambridge. So it's a very unique system, and there are about 4 universities with this kind of system in the UK, if I'm not wrong. So the importance of University of Cambridge can be seen from this, that University of Cambridge has won about 110 Nobel Prize so far, and the entire UK, the Nobel Prizes won by the entire UK so far are 135. So clearly, most of the Nobel Prize winners come from the University of Cambridge in the UK, and you can see that the total number of Nobel Prizes given in the whole world are 955, and out of them 110 is more than 12% of the entire world's Nobel Prizes have been won by people who have an affiliation with the University of Cambridge. If you talk about the legacy, there have been a lot of big names in Cambridge. For example, who doesn't know Sir Isaac Newton, or G.H. Hardy of the number theory fame, or Brooke Taylor of the Taylor series fame from mathematics, and similarly William Oughtred for log scale, he's not well known, and people who work on mechanics, they know about Maxwell equations, which were basically built by James Maxwell. Similarly, if we talk more recently, then Charles Darwin, who gave the natural selection theory, Francis Crick, and James Watson, both of whom were at Cambridge. They discovered the structure of DNA, which have, and interestingly, even the recent prize in chemistry was also given to people who were working on DNA structures. And Ian Wilmot, who was working on cloning, and the Dolly the sheep was very famous when he was working on this project. And Stephen Hawking, who passed away unfortunately very recently, who is famous for time theory and relativity, was also at Cambridge. There are so many other names which I haven't taken. For example, Ernest Rutherford, who gave the structure of atom, J.J. Thomson, James Chadwick, Robert Oppenheimer, Lord Kelvin, and so many more. And I've only talked about the science and engineering fields, people. So there are so many people who have worked in economics and are big names in the field, but I haven't talked about them yet. So you can see that Cambridge has a big legacy, and that's why anybody working at Cambridge have this pressure of continuing the legacy and continuing to do the excellent work that people here have done before. So even currently, there are so many famous people at Cambridge. For example, Sir Richard Friend, who is the director of Cavendish Lab, and he sold one of his companies, Plastic Logic, for a whopping $122 million in 2004. Similarly, Sir Tom Blundell's spin-off, which was called Aztec Therapeutics, was sold for £150 million. And Andy Hopper of computer science, who has so many famous spin-off companies from his lab and research, for example, like Cohen Computers, Real BNC, UB Sense, AT&T, and others. So why are we talking about space? When space research was at its peak, it was in the USSR era, when there was a Cold War between the USA and the USSR in 1940s and 50s, basically after the World War II. And the first rocket was launched in World War II in 40s. And that was the first time when the common line, the line between the Earth's atmosphere and the space, it was crossed by a rocket in Germany. And after that, because of this competition between the USSR and the USA, there were many space. There was basically a space race between the two. And we know that the first person to go to space, Yuri Gagarin, was launched in space in 1957 or 1957 perhaps, and then NASA was formed in 1958. And after NASA was formed in the US, they were the first people to go land on the moon in 1969. But after 1970s, the research and the work of space exploration went down, and there was no the same rigor wasn't there, and the same vigor wasn't there in this research and space explorations. But after the 2000s, after some private companies were formed and some new findings were made, for example, the exoplanets and so many other things which were really interesting people. So this space research was invigorated, and there were many other space agencies formed. For example, even recently, smaller countries like United Arab Emirates have made their own space programs, and in fact, they're doing so well that they've already launched their Moon and Mars missions, and then they're trying to go beyond in deep space. So with this, space research intensity and space exploration intensity, there's a lot of challenges as well, because there are more and more rockets being formed, there are more and more spacecrafts being formed, and there are more and more machineries being formed which have to perform different functions in space. And there are so many challenges in space, name it, from radiation protection to heating and cooling, to the time that it takes to reach from one place to the other in space because of the distances. So all these challenges have to be solved in order for the humanity to survive in space and to make a mark and to for example, live on planets like Mars. So if you talk about interstellar movements, currently we are talking about years. For example, if somebody, if we plan to go to Mars with a human mission, it is a kind of an impossible task as of now. That's because of the time it takes and many other things, for example, radiation, which I'll talk about as well. So how to reduce this time from years to hours? So there are some concepts, for example, the laser propulsion of objects with the speed of light, perhaps, or close to that, with the help of lasers. And how can we do that? And there are talks in this research, and there has been a lot of theoretical works which have proved that it might be possible to reduce or to shrink the time it takes from let's say from our Earth to Mars, from years to a few hours. And similarly, there are other risks in space. For example, the biggest risk to humanity in space is the radiation. There are so many radiations which are actually unknown. For example, there are particles, ions, and so many other galactic radiations, cosmic radiations, which are not so well known to humans. Forget about their protection. So how do we protect the humanity from these radiations? That there are radiations which directly affect your lungs, which directly affect your heart, your different parts of the human organs, and dysfunction them. So how do we tackle the radiation in space, and how do we come up with a strategy that we can go to deep space, for example, the Titan or any other planet which we believe are maybe habitable? So how do we reach there And that's a big question. So this challenge has to be solved in order for us to make a mark in space research. So then there are many other problems. For example, these kind of mechanic problems, such as the one that I'm going to talk about. So there was a space flight which was launched by NASA. It was called the Geoscience Laser Altimeter in 2003. And after it was launched with a cooling system called loop heat pipe, and which was tested on ground, and it functioned well. But as soon as it was launched, it was supposed to do a very important function. It was supposed to take 40 frames of very high resolution images in a second. So what happened is that it did not function at all, because as soon as it was launched in space, it went into a thermal runaway, meaning that the loop heat pipe device that it was installed with, it never started, basically. So it's called a startup issue. It never had the chance to function. That's why it took a year almost to reactivate it. So imagine that you spend like millions and millions of pounds or dollars on a mission, and you send it to space, and the function that it is supposed to do, it doesn't do it because of an instrumental failure. So these are the kind of challenges that we need to solve. And talking about the cooling in space, which is one of our areas that we're working on. So there are so many heating loads in space. So imagine a satellite orbiting around the Earth, and it is exposed to the radiations from sun, from albedo, from IR, and some other galactic and cosmic radiations. So in order to tackle these radiations, the heat that this satellite is receiving due to these radiations, there has to be a system which helps it dissipate the heat. But there is a blessing in disguise in space, which is that the outer atmospheric temperature in space is about 3 Kelvin, which is basically an infinite sink. So we need a device which takes the heat from inside the satellite and dumps it into this infinite sink. So for this purpose, there is a device, which is made of some materials which are steel-based materials, which were the traditional materials used for these kind of devices. And because of this steel-based material, it was never either functioning, or it was functioning on Earth and not functioning in the space where it was supposed to be. So that's why we have come up with a different solution. Before I go to the solution of why we are making what are we doing in this kind of research, I would like to introduce you to graphene, because that's what we are employing to solve certain issues in space. So first of all, graphene was extracted from something called graphite. And if you look at the history of graphite, the shepherds in England used to find some structures or some stones which they used to mark their ships, and they used to call it lead, because it was just like lead. It was soft. They could use it to mark anything, and that's why it was then called lead pencil. The pencils made with graphite, or the material that they found, was called lead pencil, although it's not a lead pencil, it's a graphite pencil, but we call it lead pencil. So because of this application of graphite, or this so-called lead, it was also implemented to make cannon balls. And since they were used to make weapons like cannon balls, so it was a felony basically in England to steal graphite from anywhere. So normal people could not have graphite or could not own graphite in that era. So that is the history of graphene, basically, where it comes from, because it comes from graphite, and that's where the graphite comes from. So if you look at the structure of graphite, the atomic structure of graphite, it's just like a stack of carbon atoms. So these carbon atoms are one on top of the other, and the bond between these sheets of carbon atoms is called van der Waals forces, which are very weak forces. It's just like you can imagine it as a stack of dollar notes. So if you separate one of the dollar notes, it's just like a sheet here, and then you can use this sheet to make balls of carbon, which are called fullerene, or tubes of carbon, which are called carbon nanotubes, or little sheets of carbon, which are called graphene. And fullerene won, the inventors of fullerene, Kroto and Smalley, they won a Nobel Prize in 1996, and the inventors of graphene won the Nobel Prize in 2010. So graphene has a lot of interesting properties. One of its properties is that it's electrically extremely conducting, and it's theoretically it's more conductive than any other material on Earth, and similarly it's as strong as nothing actually. There is nothing which is as strong as graphene. For example, if you take a saran wrap sheet thick graphene, you can lift an elephant with this little thin graphene, talking theoretically, of course. And similarly, there are many other applications. For example, recently in 2018, a professor in MIT invented a new phenomena in graphene, and he found out superconductivity in graphene. So graphene can be a superconductor, meaning that it can conduct heat without any dissipation, without any resistance. It can conduct, electricity without any dissipation or resistance. And that's one of the new breakthroughs in graphene research. So graphene is very interesting for many applications. And one of the interesting properties of graphene is thermal conductivity. So graphene conducts heat better than copper, better than aluminum, or better than any other metal. For example, the thermal conductivity of graphene is about 5,400 watts per millikelvin, and the conductivity of copper, which is the best conductor of heat after graphene, is about 3,000. So that is the kind of material that graphene is. So we employed graphene to make loop heat pipes. So a loop heat pipe is a device which basically takes the heat or absorbs the heat from a heating source inside a satellite and then dumps it to the outer atmosphere. And this is what is implemented in many spacecrafts, but they don't work. And almost 70% of the time, they have a problem in their startup. So that's why we employed graphene. The loop heat pipe is structurally, it's a very simple piping kind of a tool, but it is made of two components. One is called the evaporator, and another is called the condenser. The evaporator is basically a porous steel which is supposed to take the heat and convert the heat take the heat and convert the liquid inside its pores to vapors, which can then go to the condenser, condense it there, and then this loop continues. So this stainless steel wicks, we are trying to make it graphene based, because graphene is much better thermally conductive than the metals that they're using. Currently they're using steel. So we have made graphene based foams, graphene based 3D structures, and I'm not going into the details of how we make them because the time is very limited. So we make different graphene based 3D structures of different densities, different pore sizes, which we can tune on demand. And with this, we can make these kind of loop heat pipes which conduct or which pump the liquid much faster than the steel wicks, and which perform thermally much better than the steel based loop heat pipes. So how well do they perform? I'll talk to you in a bit. For example, this is one of the, it's basically a video, a microscopic video or image of how do these forms or 3D structures of graphene look like. So you can see these little pores. These little pores are capillary pumps which pump the liquid from the one end to the other, or so to speak, from the condenser to the evaporator, from the condensed side to the evaporation side. And because of this high thermal conductivity and so many other properties, basically, which I cannot talk about here, such as the wettability and you know, formability of graphene, we can basically have much better loop heat pipes than the steel. So this is a setup that we made with our graphene-based loop heat pipes. So this setup is according to the European Space Agency zero gravity testing setup. It's inside a big box, and we have made all these instrumentations to test the devices that we have made. I know I'm going very fast and skipping a lot of details, technical details. You can ask me any questions later on if you want. So this testing setup is used to test the efficiency of the loop heat pipes that we make with graphene-based materials. And using this testing setup, we have tested in parabolic flights, for example. These are some of the parabolic flights that we have been to, and where we have tested the loop heat pipes based on graphene. So this is our experimental setup here. So this is the control panel from where we are controlling the experiment and seeing the progress of the experiment in a parabolic flight. And this is one of the recent tests that we have done in another parabolic flight. And this is the control panel, and the testing setup is just beside the control panel from where we are controlling this thing. And this is another video of you know, this zero gravity flight, because besides doing experiment, it's a very unique experience. This is the first time that I went into zero gravity, and you know, the feeling was ecstatic, and I could not believe it. So this was the first time when I just felt the zero gravity. So besides doing the experiment and besides science, of course, there's something to enjoy as well, to see how does a human being feel in being in zero gravity environment. So besides this, so this is the result. Actually, this is the result. These are the results that we have done with the result that we have obtained with the loop heat pipes that we have made. So we have made two types of graphene-based loop heat pipes and a steel-based loop heat pipe. So as you can see that the evaporation rate, you can say that the evaporation rate is the efficiency with which a loop heat pipe works. So if you talk about the steel-based, quite evidently, more often than not, in zero gravity environment, the steel-based loop heat pipe doesn't work at all. When you talk about two types of graphene, so we can have as much as 800% improvement in the efficiency of the loop heat pipe made with graphene at different power sources. So we are using we are basically dissipating 1 watt of heat, 2 watts of heat, or 3 watts of heat. So more the heat, the more the evaporation or the efficiency of it working. So we are basically able to dissipate the heat every time. Whenever there is heat, we are able to dissipate it without any lapse. So this is the important result that we have obtained with these kind of graphene-based loop heat pipes. We have also launched, you know, I've been a part of this European Space Agency sounding rocket, in which we have launched also graphene and some other experiments. So we are doing a lot of other experiments with graphene in space. For example, how can graphene help in wound healing in space, or how can graphene help in you know, phase change materials implemented in space? How can graphene protect the humans against the radiations? So these are all the projects that we are working on. I don't have time to go through everything here. So this was the sounding rocket that we launched about a year or 1.5 years ago from Kiruna, Sweden. And so the other projects that, as I said, we're working on space suits or these kind of fabrics or textiles which protect the human against the radiation, different kinds of radiations. So this involves understanding the radiations as well, and how can we basically protect ourselves from these radiations using graphene and similar materials. So these research work got us a lot of attention from around the world, from media in Pakistan, abroad, in UK, in Europe. So we were covered by a lot of prestigious news papers. And so now I would like to talk a bit about, time permits, about our work beyond space. So we implement graphene in different applications. For example, one of the applications that we work on is mimicking human-like behaviors with graphene-based materials. So when we talk about touch-like sensing, or smell-like sensing, or taste-like sensing, these are all, types of sensings which people are trying to emulate or mimic. But among these, the most difficult sensing is the touch-like sensing, because touch-like sensing has two components. One is the spatial resolution. So humans can sense a roughness of about 1 micrometer. So if you imagine a human hair is 100 microns, so we can sense a roughness or a surface with a roughness of 1 micrometer, so which is very very high resolution. And if you talk about the pressure sensitivity, we can sense pressures as low as 1 kilopascal, which is very low pressure. So in order to make something which mimics the human touch-like sensing, we need to have these two components covered: the spatial resolution as well as the pressure sensitivity. So in this regards, we've done some work. What we have done is that we have tried to make textiles which are pressure sensitive, because textiles are conformable, they can take any shape, and they can be worn, or they can, they are basically washable as well. So we've coated nylon-based textiles with graphene, and then we have been able to prove that these coatings are washable. And I introduced this topic of graphene-based electronic textiles back in 2013. And after that, it has become a whole new field of research where people are trying to implement graphene-based textiles in energy storage, in sensing, in radiation protections, and whatnot. So initially, when I worked on these kind of coating technology, I showed the coating of graphene on all sorts of fabrics, for example, from polyester to nylon to cotton, wool, Kevlar, and glass fibers. And we were able to show them their washability as well, that these textiles are washable. So these graphene-based textiles are smart because, first of all, as I said, that it's just like a dye. You dye your clothes with graphene. And as you can see here, this is in situ electron microscopy, in which we are twisting these single fibers of fabric coated with graphene. And as you can see, 1800 degrees corresponds to about 7 times twist. And even after 7 times of twist, the coating is still intact with only a little bit of cracks, which are basically coming from the fiber itself, not the graphene. So we implemented these fabrics for pressure sensing, and we were able to sense the human blood pressure with these kind of sensors. And you can imagine the sensitivity. So this sensitivity that we got was about 20 times better than the state-of-the-art pressure sensors used for different applications. So we were able to then make a wristband out of these and do sensing as good as, that we were able to sense the blood pressure flowing through our veins. And this work was done back in 2013-14. And recently in Cambridge, we are giving the pressure sensors a new application. So we are trying to make shoe soles with these kind of pressure sensors, which we are able to connect with games, for example, a snowboarding game. So you can wirelessly play a game with your shoe connected to a game. So this is one of the applications. The main application of this is also in health sector, where you can see the footprint pressure difference of your foot for sportsmen or for people who are interested to know their walking, jogging postures. They can use these shoes to know that. And for fun, we developed this game, connected with these shoes. So, and then we also presented this in the Mobile World Congress in 2019, sorry. And we were able to show that we can wirelessly play these games with our foot with these kind of graphene-based shoe soles. And we also did recently some work in that we implemented these kind of textiles in concrete. So inside concrete, we embedded these sensors, and we were able to do pressure sensing. So if you touch this concrete, it will tell you with what pressure are you touching it with. So we tested it was from 0.1 megapascal to actually tens of megapascals. And we were able to do the pressure sensitivity with these kind of concretes. And these are the testing cycles done for thousands and thousands of cycles. So with this, you can have a bridge which is self-sensing and self-monitoring rather than installing patches of sensors in different sports. You can have a concrete made with these kind of fabrics. So the fabric is inside a concrete. If the fabric is inside a concrete, you can just take the connections out, and you can have this monitored every time and all the time, basically around the clock monitoring of these kind of structures made with graphene-based textiles. This graphene-based textile inside the concrete can also do sensing of gases, for example, toxic gases such as NO2, and also temperature sensing as well, besides the pressure and strain sensing. So in conclusion, graphene, of course, performed 8 times better than metal-based loop heat pipes when tested in space environment. And graphene can be printed or coated on literally or virtually any desired surface. And graphene textiles can make electronic skin sensors, and graphene E-textile can also make concrete very smart. So with this, I'd like to thank everybody, and I'd like to acknowledge these people, from Professor Ferrari to Carlo Iorio to Professor Kin Liao, Dr. Kamran Ahmad, and many others who I work with and who I have worked with. So I'm open for any questions. Thank you.
Okay, thank you, Dr. Yarjan, for a very interesting lecture on graphene. Yes, if you've got any questions, you could either type them in the chat box. Okay, we've got a question here. Is graphene biocompatible?
There's no definite answer to that, but there are so many studies, and there are some kind of conflicting studies where some graphene is made with different, like there are so many types of graphene, because graphene can be made from a chemical route, graphene can be made from physical route, graphene can be made from top up, or bottom up or top down approaches. So different graphene have different properties, and there are graphene which have been reported to be very good in biocompatibility, and there are graphene which have there are reports in which people have reported them to be not to be biocompatible. We ourselves are working on biological applications of graphene, for example, from cell growth to repair in the spinal cord using graphene. And from the initial tests, we believe that graphene is biocompatible.
Someone's asked, do you see it being utilized in nanotechnology and internal medicine?
Well, I'm not an expert in medicine, but there are so many studies which suggest that it has uses in drug delivery. But as I said, that we are working on different biological projects in which we're using graphene as sensors, we're using graphene as a stimulant for wound repair. So it already has applications actually.
What makes graphene sort of special? You have a sheet of graphene, yes, and if I roll that up, I can make like carbon nanotube, single wall, multi-wall carbon nanotube. If I put it together, make it like a kind of a buckyball, yes. So you got the same graphene sheet. If it's in that form, it's got better properties. But then if you roll it, you got carbon nanotubes, and it's the same material, but it's a different kind of shape.
And then different properties altogether.
Although, as you mentioned, Kroto won the Nobel Prize in chemistry for his buckyball C60 molecule.
Yes.
Mm-hmm.
Absolutely. So basically, what's interesting is the properties. I mean, when you talk about a material, the only thing that you utilize from a material is its property. For example, if you talk about steel, so steel has its strength, which we utilize. If you talk about aluminium, it has this balance of strength and weight, the density, which we utilize for different applications. If you talk about titanium, the same. And then we have the composite material. So graphene is this new class of material. Graphene erupted a new class of material called 2D and layered materials. And there are thousands and thousands of them actually. And these kind of materials have different properties from their bulk counterpart. For example, graphene comes from graphite, but it has totally different properties than graphite. So the properties are the things which make graphene very interesting. For example, I talked about superconductivity in graphene. So in 2018, a professor in MIT, along with his PhD students, they tried to do something different with graphene. So what they did is that they took one layer of graphene, they took another layer, and then they twisted them with an angle of 1.1 degrees, which they call magic angle. And at this angle, graphene became superconducting. So these are the properties which make graphene very interesting. And since it's a single layer carbon atoms connected together covalently, so it's very strong. And then we talk about superconductivity, then we talk about electrical thermal conductivities, and then we talk about dispersion of graphene in terms of inks, which can be printed on different surfaces. So these are all the properties which make graphene interesting.
And are you able to grow this graphene, in a pure form in your lab, or do you have to purchase that from companies? Or
no, we are Cambridge Graphene Centre, and we make all sorts of graphene and related materials. So it's not graphene that we make. And graphene is not the only material that we make. We make all sorts of almost 2D and layered materials with different approaches. As I said, the chemical approaches, the physical approaches. We employ all the approaches of making graphene, and we claim that we kind of make about the best graphene in the world.
Okay. We have a question here. What are the cost considerations versus benefits, say in clothing?
If you talk about the cost in graphene, it cannot be estimated now, because the thing is, if let's say that we talk about clothing and we implement this graphene coating on clothing, the amount of material that goes into the coating is in milligrams. Even for an entire t-shirt, let's say, it's in milligrams. And the cost of graphite right now in the international market is about $1 or $1.50 per kg, or sometimes even $0.50 per kg. And graphene comes from graphite. And there are routes in which 100% of the graphite can be converted to graphene or graphene-like material. So if you talk about the costs, then there are so many, estimations that you have to make. So the process that we use to make graphene how much of the energy input is there, and from those energy you can calculate the money it takes to make the graphene. Because currently the kind of research that we do, of course, we have to employ a lot of techniques in order to do this kind of research. So the products that come out of research, we spend a lot on them, because we are the first to do this kind of work. But if you talk about marketing the same thing, then you need to think differently. Then you need to think about the energy input, then you need to think about the materials that you're using, and things like that. So from materials point of view and from the energy input, in large scales, it shouldn't cost a lot. It shouldn't significantly add to the cost of a t-shirt, let's say.
Okay, there's another question here. Why is graphene not used in the third world to get clean water and solve the water crisis?
So far, I'm not aware of any technologies which are scalable with graphene for water purification or desalination or these kind of applications. So there are some attempts. There are people who have used it. They've proved it scientifically that it can be done. You can clean water with graphene, but there are no scalable technologies to my knowledge. Correct me if I'm wrong. So if there are scalable technologies in this field, of course, they will be available in the market.
There's another question. Can nano cages be made from graphene too?
So I don't know what do they mean by nano cages, but if you talk about a porous material, of course, any pore, like as I said, we make porous materials with graphene, and we can tune the pore sizes, the pore thicknesses, all the like little details of how should it look like, and what properties should it have, and how much of density should it have. So yes, I mean, if I get the question right, then yes, it can be made.
Yeah. Another question. Membranes made from graphene can be big enough to let water through, but small enough to filter out the salt. In other words, graphene could revolutionize desalination technology. Why is it not scalable?
Yes, so it hasn't been proved that it can be scalable, because the thing is, when you talk about a membrane, like the current technologies which do desalination, whether it's the reverse osmosis or membrane desalination and things like that. So there you're talking about very high pressures. So when we do the proof of concept with graphene, we are not dealing with high pressures. So that is one of the limitations that graphene has issues in scalability of this technology. When you talk about a chunk of, a big bulk of water body to be desalinated through a membrane at high pressure, then it hasn't proven to be working yet.
Okay. Do we have any other questions? If you could type them. Okay. No. Young Professional Society, obviously, we've set up to actually help youngsters with personal professional development. And there'll be a lot of youngsters who will be watching this webinar now. What advice would you give to some youngsters who are interested in getting into research, and maybe graphene is a hot topic now? Should they sort of get into, and what particular sort of area they need to sort of work where there's potential and there's good job prospects, and what would you say? What advice would you give to the youngsters?
First of all, I would like to give a very cliched and perhaps very general advice, but I think it's very important is we should all be doing things which make us happy, and if research is making you happy, then you should be doing it. And if it's graphene-based research or space-based research making you happy, then this is what you should be doing. As far as the scope of graphene-based research is concerned, I think it's moving towards scalability. So there are a lot of researchers around the world now who are looking into scaling up the production of graphene, their applications. They're looking for new application areas where they can implement graphene and then market it. So this is where the graphene research is heading towards. Even the graphene and related materials research is heading towards. And from the fundamental science point of view, as I said, you know, the superconductivity in graphene is very new. So it can be very rewarding scientifically and academically if somebody does these kind of or gets involved in this kind of research.
Yeah, we see a lovely picture of the Cambridge University there. Yeah,
King's College. King's College, yes.
Okay. Professor Ahmed, do you want to say something or ask a question before we could wrap up? I think because it's, what time is it now? Just gone 8 o'clock.
No, it was a superb presentation. I really enjoyed it. I like your emphasis that if you're going to do anything in life, make sure it's fun, because you're going to be doing it for a long time. Thank you very much. Is there any other advice you can give on in terms of skills and abilities that you need to develop to become a good researcher?
I believe that in order to become a good researcher, you need to be really interested in what you're doing. So the interest is the first thing. And if you are interested, let's say, in some topic, for example, I'm interested in employing graphene in space and to solve the problems of space with graphene. So you should then develop the skills needed in order to resolve or in order to enable you to reach the goals that you're after. Mm-hmm. So I think that's very important, that you find your interest, and whatever you're interested in, you set goals, and then you equip yourself with these skills needed to realize those goals. For example, for me, it is clearly the challenges in space, or the challenges that we face with tuning the graphene for different applications, and using the digital technologies, digital manufacturing, AI-driven manufacturing, machine learning-driven manufacturing, in order to solve the problems with the new techniques, in order not to be old-fashioned, or not to be lagging behind than the industry. So I think that's what's important, that you should set your goals and then analyze what skills do you need to realize those goals.
You started off from a very humble beginning and then reached the dizzy heights of Cambridge. What was your biggest challenge that you had to overcome?
So there were many small challenges, and one of the challenges was from my background, from where I'm coming from Balochistan in Pakistan. So the biggest challenge was that in our part of the world, there is a lot of kind of, I call it social bullying, because more often than not, people don't believe in you and what you're doing or what you're aspiring to do. So it's yourself who should believe in yourself. So forget about what other people think about you. So you need to, because you are after your dreams. You're after realizing your own dreams, not someone else's dreams. So there can be a lot of noise, everywhere, and trying to bring you down, trying to slow your speed, trying to bully you in one way or the other. But you need to, clear with your goals and be on that path which you have chosen for yourself.
I think we could have a separate interview, with Dr. Yarjan about where he was, his journey, and how he's got to Cambridge and what his future sort of goals are. But for now, for today, I think thank you very much, Dr. Yarjan, for your time, for your excellent presentation. And I'm sure people who joined us on Zoom and also who are watching us on Facebook live stream, I'm sure that they've all found your presentation very informative and very useful. So once again, thank you very much. And thank you to everyone for joining us today. I hope you've all found this useful. And we will have the recording of this webinar on our Young Professional Society YouTube channel, where you can see all the recordings of all the webinars that we've been holding. And pretty much every weekend we have like 2 webinars now. So we have one tomorrow as well. So all of them you can find on our YouTube channel. So thank you very much. A very good night to everyone, and keep safe. Thank you for joining us.
Thank you.
Thank you. Thank you.